Hi, in this video I'm going to give you a brief overview of what is linear regression. So linear regression, as you know, is more like fitting a linear line to the data points, and linear line is given by this equation y equal to mx plus b. So y equal to mx plus b, if you know the equation of a linear line, M stands for the slope of the line and B stands for the intercept. Okay, so y and x are the variables. So if you want to draw a linear line between the variables y and x, you can put it in a form y equal to mx plus b. Now m and b are the constants to be determined. Okay, and in regression we call them as parameters. So we'll see what these parameters are and how these parameters can be found out. Okay, so if you have seen what, okay, let me just okay, we'll erase this one. Okay, so here is a xy plane and we have got y and x. So this is x-axis, this is y-axis, and there may be several data points and we want to fit a regression. So the purpose of regression is that we want to generalize a pattern in the data that explains the relationship between y and x. So if y and x can be explained or can be put it or represented in a linear equation, then we can find out y when x is given. Okay, so that's basically is the intention of building a linear regression model to predict y given x, and also to see the impact on the change of x on y. Okay, so these are the two things. Okay, one is prediction of y, that's also one motivation. The second is impact of change in x. Okay, so if x changes by del x, what is the corresponding change in y? By the way, in this case y is called dependent variable and x is called independent variable. Okay, because y depends on x. So when there's so many data points, the way you would draw a regression line is the line that passes through the middle of these data points. Okay, how do we draw this line is again a question, and that's where we need to know a bit of mathematics behind how to draw a line that passes through the middle of the data points and that can represent the relationship between y and x. Okay, all right, so say for instance we have found out that the regression line is 2 plus 5x. Okay, so this is the regression line. Okay, let's assume that this is the regression line. Here this is the intercept and this is the slope. So if x goes by 1 unit, goes up, okay, so what is going to be y? What will happen to y? So if when x equal to, let's say, 3, when x equal to 3, this is 2 plus 5 multiplied to 3, right, which is 17. So this is when x equal to 3. What if when x equal to 4? Okay, so x equal to 4 is y equal to 2 plus 5 multiplied to 4, which is 22. So when x equal to 3, y is 17. When x equal to 4, y is 22. So that clearly means that the difference in the value of y is how much? 22 minus 17 is 5, and this is also 5, right? So the slope coefficient is nothing but the change in y when x changes by 1 unit. Okay, so that's how we define it. Okay, and how do we define the intercept? Take x equal to 0. When x is 0 or x is at origin, what happens to y? Y equal to 2 plus 5 multiplied to 0, which is 2, right? So when x is nothing, is 0, what value y takes? It takes 2, and that is exactly equal to intercept. So intercept is the value of dependent variable when the independent variable is 0. Okay, so this is the basic definition of intercept and slope. Regression equation. Okay. In more mathematical form, we can write the regression equation like this. Expected value is nothing but the average value, or what we are expecting from a given data set. So expected value of yi, which are a bunch of y values, given xi is given by a parameters intercept plus slope coefficient multiplied to the independent variable. Okay, so initially we said that y equal to a plus bx. It can be written in any way. We are just change the notation, alpha plus beta x. So alpha is now intercept, beta is the slope. Okay, now in more technical terms we write this as expectations of yi. Yi stands for number of values of y. Okay, and here it is xi because there are so many number of x values. Okay, so that's the representation. Okay, when we predict the values through some mathematical optimization, we change the notation slightly. Instead of yi, because xi is the real values, not the predicted values. We are predicting the value of y, not x. Okay, so x will remain same, but y will change. We call that as y hat. Okay, so y hat because these are predicted from the regression equations. Remember, prediction is nothing but some kind of a mathematical optimization using the data that's given. Remember, I was talking about passing the line middle of the data points. When you do that, you will see many data points will be lying here and there. They won't be passing exactly through the middles because it's not that symmetric. So this equation is a generalized form of the pattern between y and x. But that does not mean that it gives accurate prediction. There is always going to be some random error, and the error has to be a random error. And the value of y for each x will also be different than the actual value. So for here, x equal to lecture 2, the actual value is here, but the predicted value is here. Okay, so here when we talk about the regression line, we only talk about the predicted value. The actual value will be lying somewhere, maybe on the line or may not be on the line. Okay, so there is always some kind of a possibility of error. So predicted value is nothing but intercept plus slope multiplied to xi, and xi doesn't change because it's a given value. We all know that, and we are predicting y. Random error is just addition to that, because for each data point there will be some error, right? There's some deviation from the actual data point, and that's what is the error. Okay, and the fixed component, so this is the fixed component and this is the random component, or the component that will vary. So assumption in linear regression is that this follows normal distribution. So the error follows normal distribution. That means it will be small, there will be a large portion of the error will be mostly at the 0, and small portion here and there. Okay, and it has another property called white noise property, where the mean would be somewhere 0 and the standard deviation would be close to 1. Okay, there are many assumptions of linear regression. So linear regression assumes that the relationship between x and y is linear, which is of course as the definition suggests, y and x are linearly related. Y is distributed normally at each value of x. Okay, that's not a strict assumption, so to say. I mean, y and x need not be distributed normally, but a lot of the outcomes or results from linear regression cannot be explained if the assumption of normality is violated. the variance of y at each value of x is the same, or homogeneity of variance. That means the variation around, I mean, y values should be varied, I mean, the variance should be constant. If the variation is different at different places of x, then that's a problem, and we call that as a problem of heteroscedasticity. The observations are independent, or in technical terms we call that as IID. That means independently and identically distributed. We assume that the observations that we have taken for analysis, they are independent of each other. That means the presence of one observation doesn't affect the other. And secondly, the assumption about the data creation process is also same, in the sense that we assume that all the data points have been taken or generated from the same probability distribution. So here is what this heteroscedasticity is. We have these y values, and for each x we have some y values, right? The idea is that the variation, here is the variation, it has to be similar. It has to be similar. Imagine a case where variation will be like this. In this case, then it will be much bigger, and that's a problem. That's a problem of heteroscedasticity. So ensure that that type of data is not used for linear regression. It can well be used, but there are other ways of, I mean, the normal way of finding a regression line won't help there. There has to be some special treatment to be made first. Okay, so the question that we asked in the beginning was, how do we calculate a line that passes through the middle of the data points? You might have heard about what is known as a least square regression. So least square is something that's used. So that's an algorithm. Ordinary least square is the algorithm. Simple algorithm. There is a perfect solution to a least square method. There are other ways to find out a regression line. It's not the least square that's the only way to find a regression line. Here is here is a very brief description of how you see the least square to be of making sense. I mean, some intuition behind it. Okay, so the idea here is that we have the average value of y values. Okay, so we draw this line. So each data points will be different from its average value. That some kind of a variance, right? Isn't the variance is the square of the distance of the observations from its mean, right? So that's the total variation. So total variation in the y, because the idea in linear regression is to see how much the x is able to explain the variation in y. The total variance in y is given by yi. How yi, each data point in y is different, or how far it is from the mean. So take the square of that, is equal to the predicted value of the variance and the error term, some kind of a residual, or we call that as error term. Okay, on the picture you can see the total variance is this one. Okay, so B is the predicted variance and C is the residual variance. Okay, so in other words, we can see that the total variation that we can see has two components. One is being explained, the other is not being explained. So B represents the portion of the variance that's being explained, and C represents the portion of variance that's not being explained. Okay, and there is always going to be some variance which won't be able to explain. Okay, and the more the B is, the better is the model. Okay, so we calculate some kind of so this is more of some kind of, we call that as R square, where we want to know how much variance is being explained in the y variable, which is the dependent variable, by this model. Okay, and the greater the B is, the better it will be the model. Okay, and this ratio would tend to be close to 1 when the entire variance is explained by this model. Here's an example. So there is some hypothetical data on some some data. So it's on some 100 middle-aged old European men and the presence of vitamin, something like that. Okay, so here is the data. It's the dependent variable, the distribution of vitamin D, that means presence of vitamin D in people. And in the first thing you do when you sort of prepare yourself to build a regression model is to find out the distribution of each of these variables. If you're closer to the normal distribution, then your task is much easier. So here you can see it's not normal but nearly normal with some fat tail on the right hand side. You do that for other variables also. This is pretty normal, and there are two variables. Okay, so basically your vitamin D percentage um, is going to be regressed with DSST. So we want to know how these two are related. So if DSST is given, whether we will be able to predict the percentage of the vitamin D. All right. So several data sets, and we will see how a regression line can be fit into these data sets. If you see the first data set, there seems to be no relationship. Why? If you see the pattern in certain way, if if the y value doesn't change with x, then there is no relationship. Okay, this is more of a circular, right? It has to be the linear straight line. There's no relationship here, it seems, because if you see that the y value doesn't seem to change with x. Here there is some relationship, there is some upward relationship I can see, but again it's a weak relationship because the data points are very highly varied, so they're not closer to the middle line. Somewhat better relationship we can see. Now you can pass the regression line. This is again much better. You can pass a regression line which passes through the middle of the data points. So when there is no relationship, you cannot have a regression line. Okay, the slope will be 0 in that case. If you fit a straight line that is parallel to the x-axis, the slope is 0, right? That we know from the coordinate geometry, that a linear line that it is parallel to the x-axis has a slope of 0. So it can't be then called as a regression line because slope is anyway 0. So we just have the intercept, right? So that's just taking the average. So that's nothing but just taking the average of the y values. All right. For the second data, you see some relationship, but that's not significant relationship. Okay, you see that expected value of y is 26 plus 0.25 into vitamin D. Similarly, here you can see slightly better, some relationship 1.2 into vitamin D. Okay. Next, you can see, so you can see a pattern. The intercept is coming down, the slope is going up, right? So that's an ideal case of having a better relationship. We were more interested in knowing the slope. That talks about the relationship between y and x, or here DSST and vitamin D. Okay, so significance test or hypothesis testing is an important part of linear regression. It's a separate topic altogether, but I'll talk in brief. Okay, so hypothesis testing tests the fact that whether the coefficients that you have received, whether slope or intercept, they're statistically significant. Okay, in a layman terms, if let's say you get the slope to be 0.03, now this seems to be a number that is greater than 0. But is that greater than 0 statistically? Because mind it, you are doing your analysis on sample data, but you do not quite know whether that sample is pure representative of population, because in population data could be entirely different. So 0.03, having a coefficient value of 0.03 need not necessarily mean that there is significant relationship. It could be very equal to 0 and hence need to be verified first. No matter what value you get, you have to ensure that you statistically verify that it is significant. Significant means it's not zero, it's not close to zero, equal to zero. So basically it says that the null hypothesis says that the beta 1, the slope, is 0, otherwise it is non-zero. So when it's 0, there is no relationship, linear relationship between y and x, and when it's non-zero, then there is some linear relationship. So you calculate the t statistics, you just take the beta, subtract 0, which is nothing but beta divided by its standard deviation, and then look at the t distribution table, and take the threshold value at maybe 95% confidence interval, and the if the probability that it is you can get the p values from there is less than 0.05, then you consider that as significant. That means you can go ahead with explaining the value. Okay, otherwise it is close to 0, or it is 0 in fact. Okay, no matter, it might look non-zero, but statistically speaking that's as good as no relationship, hence it can be considered as 0. So if it is not significant, then we go ahead with the null hypothesis, which says that the beta is 0. Otherwise we just reject the null hypothesis and accept the alternate. So for our case, at 98% confidence, we get the p value to be 0.001, which is less than 0.05. Hence it's significant, and it's significant. Alright, so far we have seen what is known as a simple linear regression. That means just we were dealing with just one independent variable. X is the only independent variable, but we can extend that to more than one independent variable. Okay, we can have x1, x2, x3, as many number of independent variable as you possibly can have. So we can include more variables, we can include age, we can include many other things. So here we have just include, apart from vitamin D percentage, we have included age. So now we have got independent variable 1, x1, this is x2. But you will have most of the times only one dependent variable, but there could be several independent variables. When you have more than one independent variable, visualizing is somewhat different, right? Or difficult rather, because you won't be able to visualize in a 2D plane. It has to be again a 3-dimensional plane. So here is y, and there are here so there are now two xy planes, right? XYG planes. So this is G, and you have XY. So age and vitamin D at other segments. Here it is age, here it is vitamin D. Okay, and more than 3 dimension, it is very difficult to again visualize. Okay, and then the origin will be somewhere here. Okay, and here instead of lining a regression line, you will be drawing a regression plane. 2-dimensional regression plane, which will look something like this, right? I am not good at drawing, but yeah, something like this. So now this plane passes through this data points. Similarly, you can construct something like this. This is also a plane, right? So instead of a regression line, now you need to fit a plane. Okay, using the same, we can just calculate the value of intercept and slope, and check whether p values is significant in both cases. It has to be less than 0.05. Yes, it is. So both are significant. That means both contribute towards the variation in the DSST score, which is the dependent variable. So in summary, we can say that multiple linear regression has more than one predictor or one parameters. So how do we explain then the betas? Well, each regression coefficient is the amount of change in the outcome variable that would be expected for 1 unit change in the predictor if all other variables model were held constant. That means Last time we explained what beta 1 is. We explained that when x goes up by 1, that's the corresponding change in y. But now we have several of them, right? So the way we explain is that if you keep other constant, what is the change when x goes up? Okay, and then you, for example, you started with this one, then you went to the next one, you keep other constant. So beta 2 is nothing but if you change w by 1 unit, what is the corresponding change in y? Okay? So that's also known as marginal effect in technically speaking. Okay, thank you.